Hi everyone, this video is the solution to example 2 on plastic section properties. This is a much more interesting exercise than the previous one because now the section is singly symmetric, which means the centroid will change position when we calculate the elastic properties and then the plastic properties. But okay, as a little bit of a revision, let's start with the elastic section properties. And for this, we know we need to calculate Ixx and we need to calculate Ymax, similar to before. But to calculate Ixx, we first need to find the centroid. So if we calculate Yg measured from the bottom, knowing that this is just the sum of the area, so let's split this in two squares. So this red square here, and then the green one on the top. So if we do the red one first, the area is 20 times 150, and then the position of the centroid from the bottom is 75, right? So this position measured from the bottom is just 75. And now we're going to add the other area, so 100 times 20, and then the position of the centroid will be 160, so 150 plus 10 to give you this coordinate of that point. And this we divide by the total area, so that's 20 times 150 plus 100 times 20. If we put this in the calculator, we get that the centroid is 109 millimeters. So that means, and now we're going to delete all of this, that means the position of our centroid, let's call here, is 109 measured from the bottom, 109. So now we can calculate Ixx, and again, let's split this into two squares. Let's do the bottom square first. So for Ixx is base times height cubed divided by 12. So 20 times 150 cubed plus 12 divided by 12 plus, and now area, so 20, 150, and now a distance squared between the two centroids. So that should be 109 minus 75 squared. So 109 minus 75 squared. And now we need to add the other rectangle, so that will be 100 times 20 cubed divided by 12 plus 100 times 20 times, and now the distance between the two should be 160 minus 109 squared. And if you put all of this in the calculator, we should get 14.4 times 10 to the 6 millimeters to the power of 4. Okay, this is looking good. Now the only thing we need is to calculate Ymax, and Ymax, knowing that the centroid will be at 109, Ymax will be 109. So again, Ymax is nothing more than the maximum distance from the centroid, either to the top or to the bottom. So in this case, Ymax is the bottom one because it's larger, okay? So we assume to be 109. So Ymax is 109 millimeters, which now means that our elastic section modulus is 14.4 times 10 to the 6 divided by 109, which is equal to 132 times 10 to the 3 millimeters cubed, okay? So that's our elastic property. And again, guys, what does this mean? It means that a moment, the resisting moment elastically, will be nothing more than our elastic section modulus times Fy. And in this particular example, we are given that Fy, so the material yield stress, is 250. So we can calculate that our resisting moment in the elastic range is 132 times 10 to the 3 times 250. And now if we're careful with the units are Newton per millimeter squared. So that means our final unit will be Newton times millimeter, which is a normal unit for a moment. So it's looking good. So by the end, this will give you 33 times 10 to the 6 Newton millimeter, which you can say that is 33 kilonewton meter. Okay, so it's looking good so far. We calculated the elastic resistance of this section, assuming the material can resist 250 Newton per millimeter square. But what are we exactly calculating? We just calculated that 33 will cause, again, the yielding of a particular section. So let's draw again our section, and please make sure this makes sense to you, because this is probably the most important diagram on this topic. If this makes sense to you, the rest of the topic will be very simple, because that's the part you need to remember. So we figured out that the centroid is at 109 millimeters from the bottom, but the centroid has a particular property. Under a certain moment, m, the centroid has stress of 0. So if we think about the stress diagram here, and let's assume we get compression on the top, and we get 0 in the centroid, the diagram we're basically obtaining is this one. Okay? And as you guys can see, because the centroid is slightly shifted to the top, the stress on the bottom is larger than the stress on the top. So that means this sigma here won't be Fy, but this one will be. So sigma max will be at the bottom because it's at the bottom that Y is equal to Y max. Okay? If you remember from the beginning, we said that Y max is 109. That basically says that the maximum stress will be at the bottom. So what we just calculated is when M is equal to 33 kilonewton meter, right? When M reaches this particular number, the first stress here, the bottom stress, will be equal to Fy, which again means that this first fiber here, right? This fiber here will plastify, but only this, okay? Nothing else will plastify, just this one. So what we're basically interested in calculating now is what will happen to our section when everything plastifies. So now before we go into the full plastic behavior of the section, I just want to show you what would happen in between the two. So if you guys think about the spread of plasticity, you will see that more and more of the section will get equal to Fy. So let's say this amount of the section will be equal to Fy. And only then, let's say the top one will be also equal to Fy. Let's say something like that. There is an intermediate step between fully plastified and just one fiber plastifying that we usually don't calculate, but I just want to show you what this means. Is if the plasticity is increasing on the bottom, necessarily the centroid, so the place where the stress is equal to 0, necessarily needs to change. And what happens is that it shifts up. And we're going to learn how to calculate that as well. But eventually, we're going to get to a point, and that's the point we're interested in calculating, where the entire section will be equal to Fy. So here Fy, and let's say maybe a little bit more, and then it goes to compression, and then the entire fiber of the beam will be under compression. Okay? And this is exactly what we're trying to calculate here, this plastic, so let's call it fully plastic behavior. Okay, so let's have a look now. How do we learn how to calculate the properties under fully plastic behavior? So the first thing we need to learn is that these two forces, again, are equal to a force in compression and a force in tension. Okay? And if you guys want to think about how we calculate this, let me draw again the section next to this. So if I draw the section here, so if I draw the section next to the diagram, what we're interested in calculating is this point here where the compression becomes tension. So above this line, you're going to get compression, and below the line, you're going to get tension. And basically, we're very interested in finding the coordinates of this line. Let's call it the plastic centroid, okay? Maybe the other way around, YG plastic. And how do we find this YG plastic? We find by assuming that if FC is nothing more than Fy times the area in compression, and the force in tension is nothing more than Fy times the area in tension. And again, we can do this because the entire stress, all the points in this section, have a stress of Fy. The way we find this quantity, this line, is where the area in compression is equal to the area in tension. And why do we do that? We do it because if we want horizontal equilibrium to be respected, we need Fc to be equal to Ft. Otherwise, we don't have equilibrium in this section. So Based on that, we're going to find where is the area of compression the same as the area in tension. This is nothing more than saying that the area of compression is nothing more than the total area, so let's call it like this, divided by 2. So now, what is the total area? The total area is, let's say, we calculated this before, so the total area is 20 times 150 plus 100 times 20, that's 5,000. So that means the area in compression needs to be half of the total area. So if this is 5,000, the area in compression needs to be the same as the area in tension and needs to be 2,500. So basically, we're saying that this green area needs to be 2,500 and then the red area needs to be 2,500. So we can say that the green area is nothing more, so maybe it's the easiest one, than this thickness of 20 times this value of YG plastic. So if we do that, 20 times YG plastic equals 2,500, we can calculate that that coordinate is nothing more than 125 millimeters. Okay? And we can stop here to confirm that the plastic centroid is indeed higher than the elastic. So before we had 109 and now it's going up. So that means we reached 125, and that goes along with this theory of the plasticity, spreading through the bottom first and then reaching the top after. Okay? Okay, so we find this 125, and now the only thing we need to do is to calculate the plastic section modulus. So again, Y plastic is nothing more than taking this force in compression and multiplying by this distance, and then taking this force in tension and multiplying by the distance to the centroid. So let's do the one in tension first because it's easier. So if we do Ft is nothing more than Fy. So let's remove the Fy for now. Let's just do it At. So it's area in tension. That's 2,500 times, and now the distance is 125 divided by 2. That should give me this distance here to the centroid. And now I'm going to add the part in compression. And now the part in compression, we can do it all together, but it's a little bit complicated because then we need to find the centroid of this red region, which is not ideal. What we're going to do is we're going to split this in two. So we're going to do first this bit and then the top flange bit. So let's do first this central part of the web. So here, the area is going to be 125 is that dimension. So if we check, the total is 150. So this little bit here is 25. So let's do 25 times 20. And now we multiply by a distance, which is 25 over 2. Distance between that centroid there. And then for the top one, the top area is 100 times 25. Let's confirm the dimensions. No, it's 100 times 20. And now we multiply by the distance, which is 25 plus 10, so it's 35. And if we add all of this up, we should get that this is equal to 232.5 times 10 to the 3 millimeters cubed. Okay, and now we find the plastic section modulus of the section. The last step is nothing more than getting the resistance of the section. That is equal to 250, so Fy times the plastic resistance. So if we multiply this by 250, we get this is equal to 58.1 kilonewton meter. So what we found out in this exercise was that this first section that we started with, and it has a material of 250, once the moment gets to 33, this moment here, we get the first fiber that plastifies. In this case is the bottom fiber. But then that doesn't mean that the section is done, that it's going to break immediately. There's still capacity. The section can still get the load, and the section will find a way to resist the load. So an intermediate step, let's say here in the middle, that's a moment of 33. An intermediate step, let's say for a moment of 40, will cause some of the section to plastify. In this case, all this bottom part will plastify, but then also the first fiber on the top will plastify. But again, we still have a lot of section that is sound, and that could be used to resist more load. But eventually, when we get to this stage, and this is the moment we just learned how to calculate of 58.1, once we get to this moment, now the entire section has plastified, and that is the theoretical capacity of this section. Okay? So besides knowing how to calculate these things, what's very important to remember is these three graphs. Okay? The sections have different behaviors. They have an elastic behavior, they have somewhat a semi-plastic behavior as well, and then they have the fully plastic behavior. And only when we get to this stage, we get what we call a plastic hinge. So the section becomes malleable, kind of like Play-Doh, and it can't resist any more load. Okay? So that's the idea here on how to solve these problems. I hope this made some sense. I hope you enjoyed the video, and have a nice day.